You've probably heard the saying, motion is relative. Or perhaps you heard people speak about Einstein's theory of general relativity and Einstein's theory of special relativity. But what is this concept of relativity? In short, the concept of relative motion or relative velocity is all about understanding frame of reference. A frame of reference can be thought of as a state of motion of the observer of some event. For example, if you are sitting on a lawn chair watching a train travel past you from left to right at 50 meters a second, you would consider yourself in a stationary frame of reference. From your perspective, you are at rest, and the train is moving. Further, assuming you have tremendous eyesight, you could even watch a glass of water sitting on a table inside the train moving from left to right at 50 meters a second. An observer on the train itself, however, sitting beside the table with the glass of water, would view the glass of water as remaining stationary from their frame of reference, because that observer is moving at 50 meters a second, and the glass of water is moving at 50 meters a second. The observer on the train sees no motion for the cup of water. To give frames of reference a more simple example, let's observe the video here. In this clip, we can tell that the ball is moving relative to Znab. Here we cannot determine who is moving relative to what due to the lack of frame of reference. And in the final clip, we are able to determine that the Znab is moving due to the new frame of reference provided by the lockers. In most cases, the Earth makes a terrific frame of reference. However, there are times when calculating the velocity of an object relative to different frames of reference can be useful. Imagine you're in a canoe race, traveling down a river. It could be important to know not only your speed with respect to the flow of the river, but also your speed with respect to the riverbank and even your speed with respect to the opponent's canoe in the race. Dealing with these situations, you can state your velocity of an object with respect to the reference frame. For example, the velocity of object A with respect to reference frame C would be written as VAC, even if you don't know the velocity of object A with respect to C directly, by finding the velocity of object A with respect to some intermediate object B, and the velocity of object B with respect to C, and can combine your velocities using vector addition to attain the equation VAC equals VAB plus VBC. At this point, you may be asking yourself, how many frames of references are there? Well, that's the beauty of it. Everything and anything is a frame of reference depending on what situation it's in. The computer you're watching this off of, that building you're standing in, or even the Earth itself rotating in the galaxy is a frame of reference that we can use today. Hopefully I've left you with a better understanding of frames of reference and how it affects us in our everyday lives. Thanks for watching.
Could you tell me in which of the two clips the vehicle is moving? And while you're thinking about the answer, let me explain what a non-inertial and inertial frame of references are. A non-inertial frame of reference is when an object is accelerating, and Newton's first and second laws are not valid. Inertial frame of reference is when an object is at rest or in uniform motion, and Newton's first and second laws are valid.
If you guessed clip 1, you're correct. But because you were in the passenger's frame of reference, both answers were technically correct. This is because if the passenger sees the vehicle moving at a constant velocity, it's just as though the vehicle were parked. Because a parked vehicle is at 0 meters per second, which is a constant velocity. A person from outside would see the vehicle moving because their frame of reference is not the same as the person in the vehicle.
Now let's see how a helium balloon reacts in a car as the car accelerates, comes to a stop, and turns around a curve. In the clip you just watched, you can see how the balloon reacted when the car was accelerating. The passenger, in this case, would be pushed back into his seat, whereas the balloon moved forward. This is due to the movement of air towards the back of the vehicle, creating an area of higher air pressure. And because helium is lighter than air, it wants to float away.
In this case, the opposite occurs. As the vehicle brakes, it goes from a constant velocity and begins to slow. The balloon moves backwards because of the movement of air towards the front of the vehicle. This causes the air pressure to increase in the front and the balloon to move away, as again, helium is lighter than air.
As the car turned the curve, you can see how the balloon tilted outward toward the window, whereas a passenger would tilt inward. And this is due to, again, the air movement within the vehicle. Now, after watching those clips and how the balloon reacted when the car accelerated, came to a stop, and turned around the curve, you may think there's an external force acting on the balloon, when there's actually a fictitious force. What is a fictitious force? Let us explain.
A fictitious force is a force that only occurs in a non-inertial frame of reference. This is because of the acceleration in a non-inertial frame of reference. The acceleration causes the vehicle to move faster, and all the objects in the vehicle to move faster once they have been pushed by the vehicle. So at first they remain at the constant velocity and the vehicle moves forward without it. So they are pushed backwards. Unlike the helium balloon, which is repelled by the air that is increased in pressure because it moves backwards as well. So the balloon will act opposite to the fictitious force because of its properties.
If you've been in a commercial airliner, you might remember feeling pushed back into your seat when the airplane took off. You may have felt the same feeling in an accelerating car. Now remember that feeling and take a look at the compass on screen. The sound has been muted and the background mostly obscured. What you see is the current heading on the compass card. Now watch the video and see if you can figure out how the vehicle the compass is mounted in is moving. Try to estimate the change in direction and the acceleration. If you guessed the vehicle was turning, you're wrong. In fact, the vehicle moved straight down a line drawn on the ground. More importantly, the vehicle's acceleration at the start was increasing, while near the end the vehicle's acceleration decreased as it came to a stop. Now the same video will be played, but with sound, and the new information you now have. As you can see, the compass indicates a turn while the airplane is moving in a straight line on the ground. Now what causes this and why is it important? Because of the construction of the compass, one end of the magnet is dipped down compared to the other. The angle of the dip is measured from a pivot point. When the aircraft accelerates, the acceleration acts on the pivot point, while the resulting fictitious force acts on the center of the gravity of the entire magnet. This produces a turning moment, causing the compass card assembly to rotate, even though the aircraft isn't turning. In the northern hemisphere, the compass rotates towards the north, and the opposite in the southern hemisphere. This also occurs when an aircraft decelerates. Here the throttle is closed and the aircraft begins to slow down. As the acceleration decreases, the compass shows the error. However, once constant speed is reached, the compass acceleration error is corrected. Note that the aircraft doesn't need to be flying straight and level. In this clip, the aircraft is ascending at approximately 800 feet per minute straight towards the runway, but since the rate is constant, the aircraft becomes an inertial frame of reference and isn't affected by the fictitious forces present in non-inertial frames. So in summary, when an aircraft accelerates or decelerates, it becomes a non-inertial frame of reference, which is subject to fictitious forces. One side effect of these forces is the compass acceleration error, which can cause significant errors in navigation, and in fact inspired the invention of a new instrument, the horizontal direction indicator, which uses a gyroscope to eliminate this error. Even with the onset of new instruments and the use of GPS, this error can be fatal, as it almost was in this case.
The pilots had landed at Taney Airport, radioing controllers at Branson to alert them of the mistake about 7 miles from their intended destination.
The fact that they're only 6.5 miles apart and there was just a couple degrees of difference for the orientation of the runway, that adds to the confusion.
The plane landed on a much shorter runway than it was supposed to, nearly half the size. Passengers on board say they could feel the brake slam, only to find out later their plane stopped around 500 feet short of a steep drop. No one was hurt, but flight experts say the outcome